So, good afternoon, everybody. We started where we left yesterday, and just as a quick reminder, what I will be focusing on is how internal symmetries are required to discuss hadron structure and how ultimately these things led to the appearance of quark model. But here I required a little bit of mathematics, and as Professor Shastri asked me to give some technical details, especially from students' point of view, I think this is going to be quite useful. Though, of course, questions on these things can always be taken again later on. And if they have done few things already in their class very well, then probably they will enjoy more. Particularly, I am actually referring to angular momentum algebra. So, just as a just passing time to let the other join. So it is basically a reminder what we did last time, that mesons, because there is no problem with lepton, matter particles are divided in two category, leptons and hadrons. There are 6 leptons, all of them at least up to the present energy scale. That means around 10 to the power minus 16 centimeter or 10 to the power minus 18 meter. They look quite like. They may have any structure, but we don't need at the moment. There is no experimental evidence. However, in contrast to that, mesons and baryons, they have sufficiently large radii around a Fermi scale. So that shows that they may not be fundamental. They are actually not fundamental. But the interesting thing is there were so many particles. People found that if you fix the spin and parity quantum number of a particular set, they seem to form, mesons particularly seem to form octet plus singlet pattern. For example, this k plus k0, pi plus pi 0, pi minus eta and k0 bar and k minus, they form octet along with eta prime. And you also see their mass is around, say, 400-500, quite close to each other. And separately, Ks seem to be quite degenerate. They have mass around 495. Same thing is true for pi, mass around 140. So they obviously seem to respect symmetry, which I will talk about in quite detail. That is isospin symmetry, which is quite similar to ordinary spin symmetry mathematically. Physically, they may different. A similar behavior was also found in vector mesons. You have Ks, rhos, and K star antiparticles, and so phi. They also form a nonet. And a similar thing was found for baryons. Say, for example, lowest spin baryon spin half plus form octet, whereas their excited state spin 3/2 quartet spin, they form a group of a set of 10 decouplets, we call them technically. So again, we find here that proton, neutron are quite degenerate, quite close to each other. And sigmas, sigma plus, sigma 0, sigma minus, again are close in their mass. And same thing is true about xi 0, xi minus. So whenever we have this kind of a degeneracy, it may be exact, it may be approximate. It seems to indicate presence of some symmetry, which is technically isospin here. So same thing you find in decouplet also, that deltas, sigmas, and xi's and omega, they form isospin quartet, isovector, iso doublet, and isosinglet. So this is where we left yesterday. And then and this is the main theme of today's talk, role of symmetries. I keep on actually reminding you, symmetries are not given proper attention. They need to be taken more seriously. In fact, everywhere I find only symmetries leading to various things. For example, first thing is the degeneracy. Whenever degeneracy of states means you have many quantum states, eigenstates having mass equal or energy equal. So if that is so, we say it is exact symmetry. But even when there is a small discrepancy, we call it approximate degeneracy, and there are reasons behind that approximation, or particularly technically called breaking of the degeneracy. That is what I will touch. And then symmetries also lead to conservation laws. These conservation laws may be external, may be internal. External by external, I mean conservation law connected with space-time. For example, conservation of energy, conservation of momentum, conservation of angular momentum, even even parity, for example. These are associated with space-time, and they are always honored. Parity, you leave aside for the timing. At least the conservation of energy, momentum, linear momentum, and angular momentum are strictly honored. Then, as an example of internal conservation law, I can give you charge. Charge, in any process, electric charge is always concerned. One can say that this is consequence of internal symmetry given by technically global gauge invariance. But this gauge symmetry is also found to be responsible that to dictate the dynamics. What do I mean by that? I mean by that is who tells that Coulomb law should be like that? This is actually a consequence of gauge symmetry. Little bit of gauge symmetry, gauge invariance. I'm sure students might have learned in BSc, yeah, particularly. I mean, certainly so in the master's, even if they have there. So this is what I will focus. This is the last portion is a little more more technical. So I will take up this issue when I will be talking about unification of fundamental forces. But let me show how simply these first two things can be obtained. So how symmetry lead to degeneracy? I'm talking about elementary particle, which are essentially quantum mechanical systems. So I'm restricting from that point of view. So let a quantum system is described by a Hamiltonian. What do I mean by that? It means that Hamiltonian is acting like an eigenoperator, and it is giving us eigenstates given by psi, and of course, if corresponding energy eigenvalues are E. So this is what we normally solve, say in case of Schrödinger equation, or even when we go to relativistic quantum mechanics, we deal with Dirac Hamiltonian. So we have Hamiltonian, which is usually constructed of two parts: the kinetic energy term and the potential energy term. And now suppose we have a symmetry operation which is honored by the quantum mechanical system. First of all, let this symmetry operation be unitary. People sometimes are scared of unitary transformation, but we know rotations in real dimensional spaces. So these are nothing but a rotation in complex vector spaces. That is as simple as that. So suppose we have a unitary operator. What do I mean by that? In case of rotation or orthogonality, we have a orthogonality condition that inverse of the rotation is given by its transpose. So in complex vector space, this condition is replaced by unitarity condition that you conjugate, that means transpose and complex conjugate done together, that behaves like the inverse of the operation. So if we have a unitary transformation, which what it does, it connects different states of the same quantum mechanical system. So suppose you apply this operator U upon this state psi, you get a new state psi prime. Obviously, this psi prime state also belongs to the same quantum system, but in general, it may have a different eigenvalue. E may be different from. However, if this unitary operator has a special role, and what is that? It commutes with the Hamiltonian. More technically speaking, you know, states are transformed with the help of unitary operator like this, whereas you know that operators are transformed like this: U operator and U dagger. So Hamiltonian is applied with this U in this way. We apply U on left and U dagger on right. If it leads to the same Hamiltonian, that means the quantum mechanical system is honoring the transformation which are given by described by this unitary operator U. So now this U dagger can be replaced by U inverse. So that is where we need the unitarity, this condition. So if you do that, then simply apply U on right on both the side. So that will give you HU equal to UH, or simply saying that U commutes with the Hamiltonian. So anyway, either you use this language or this language or those language, to me, they are, they all mean the same. Then it is a very straightforward application of this vanishing of the commutator upon the state. That is, suppose I apply the Hamiltonian H prime, which we know it gives the energy eigenvalue E prime. Now the psi prime can be replaced by U psi here, and because H commutes with U, so HU can be replaced by UH. So H, after coming here, acts upon the original state psi, give you the energy eigenvalue E, and this E is a number, complex number. So you can switch it here. So E multiplied to U psi is nothing but psi prime. So what do we learn from this thing is E prime is equal to A. So this is nothing but degeneracy of states of that quantum mechanical system. We need not worry about that all states may or may not uh, honor this kind of a symmetry. Sometimes a subset of states may honor, sometimes a bigger state is honored. This is what we slowly explore. I hope students have understood this point, because this is little technical, but of course it is a textbook material now. So you can always find it to that. So this is how degeneracy is a consequence of a symmetry of the system under particular transformation given by some unitary operators. So in ordinary space, these are like actual rotations. So with these, we come to the second consequence, that is symmetry and conservation. Here I have to remind you of the Heisenberg picture. You know, there are 2-3 pictures of the quantum mechanics: Schrödinger picture, Heisenberg picture, and also the Dirac picture. The typical difference between Schrödinger picture and Heisenberg picture is, by the way, picture don't mean that they will give you different physics. Physics remain the same. So either you can use the Schrödinger picture or the Heisenberg picture. What is the difference? In a Schrödinger picture, operators don't change in time, but wave functions or wave vectors evolve with time. But in Heisenberg picture, it is the operators which evolve in time, and state vectors do not. In Dirac picture, which is also known as interaction picture, we divide Hamiltonian in parts. One part is used to evolve the state. The other part is used to evolve the operator. So it is like a mixture of the two. So in this way, we know that operators, the time rate of change of operators are, that is essentially given by its commutator with the Hamiltonian. Recall in Schrödinger picture also, it is the Hamiltonian which is responsible for the time evolution of states. I hope everybody remember here that IH d psi by dt, that is time derivative psi is nothing but h psi. So that is what we solve as the time evolution. And just as a remark, when we look at physics, most of the time that is what we find. We are quite often interested in time evolution of certain properties of the system or behavior of the system, or we are also sometimes interested in the spatial distribution. That is where calculus comes to our rescue and gives us a differential equation, ordinary type, or the partial differential equation. So this is what most of the time we do in physics. So in Heisenberg picture, time rate of change of an operator is given by 1 over eta h. H cross is Dirac constant or Planck's constant divided by 2 pi multiplied with the commutator of u and h. Of course, I must be little cautionary here, because this is true when u is not explicit function of time, and most of the time we have that kind of operators. If it is explicitly dependent upon time, then there will be a partial derivative of u coming over here. All these things I hope I will be able to get the opportunity to talk in the series of lectures on quantum mechanics, because this is essentially quantum mechanics. So if you commute with the Hamiltonian, obviously the right hand side goes to 0. So you have du by dt, that time rate of change of u is 0. So it immediately tells you that u is a constant of motion, but more formally speaking, it is the physical quantity we are looking for. So which is given by the expectation value of this operator between the eigenstate of the system. So this is what we always measure. We neither measure psi nor measure u. These are not physical object, but this expectation value, that is psi bra, psi u, psi ket, it is nothing but volume integral of psi star u and psi, that is, it is a physical quantity. So since psi in this picture don't evolve in time, so if du by dt is 0, so time rate of change of this expectation value will be 0. So therefore, this physical quantity will be constant of motion. That is nothing but a conservation law. So I have shown you two important things: how symmetry leads to a degeneracy of states of a quantum system, and also how it leads to conservation law. As I told before, the dynamics part I will cover up. I will discuss in a separate talk on the fundamental forces, because that is what I need in order to solve quantum electrodynamics. In fact, that tells you, there we will learn how gauge symmetry tells you what should be the nature of electromagnetic interaction. So I will give you a little reminder, because sometimes I find students having little difficulty in evolving in a learning group theory, and often I tell them they don't have to really worry, because they have been taught group theory right in I think 6th or 7th class, or maybe earlier, because now I am having a niece who comes to me for 6th class lecture in mathematics. There I find that already NCERT has done a good job. It introduces fundamental aspects or postulates of a group without naming a group. So I wish to remind you that all of these students which we are having now must have done these postulates or active properties. These are the properties of closure, associativity, identity, inverse. So you can choose any set. What is group is? It is nothing but group is a set of objects, also called elements, say A, B, A, C, any pair of which can be combined. So what we need is an actually operation. It may be addition, it may be ordinary multiplication, it may be other form of operations, like when we are dealing with permutation groups, then we are permuting the subject. When we are dealing with the transformation, say for example, rotation, combination law means application of successive transformation. So the language of operation may keep on changing, but the whole purpose behind the operation is we should be able to combine two elements of the group. So it is not much, not less. So this operation is such that it satisfies the following four postulates. If you are those are smart might have seen that commutatively I have not included here, whereas because when we see the class 6 or 7th mathematics, even probably earlier, they also introduce commutativity. Commutativity condition is not a compulsory condition for a group to be there. So we need only four conditions which are technically called group postulates. First is closure. That means product of two arbitrary elements, say A, B, is a unique element of the set. So we are living in the same bag. Suppose I have the bag of the elements and I combine any two elements in the bag. I enter with some element, of course, lying within the bag already. So this is what we see. So AAB, by the way, this multiplication is not necessarily multiplication. As I mentioned, it is just an operation. You can define it in many complicated ways as time goes on. It's up to you. And then the condition of associativity. The order of multiplication for composition of the elements is actually a material. So when you say we want to multiply A, B, AC, you can do it in, for example, in two ways. You combine AA with AB first, and then you combine it with AC in this order. And then, or you can combine AB and AC first and multiply this by this A like this. So the result is going to be the same. So that is associativity. And then there is a unique element which we call identity, which such that when it is multiplied or combined with any element, it does nothing. It keeps the other element as it is. And lastly, for every element A, there exists another element that is A inverse within the same bag, which satisfy the following condition. That is, when you multiply AA with its inverse, or AA with its inverse, or its inverse with itself, you end up with identity. And so, for this condition should be satisfied for all the elements. So, whatever these conditions are, all the conditions are honored by all the elements of the group. So, it is as simple as that. So in that way, I find this is something which every student must have done in their earlier classes. Incidentally, the only thing is NCERT mathematics book or maybe other books at that level do not use the word group, but they certainly make us realize that it is integers which form group under addition, and rational numbers also form group under multiplication. We carry this behavior for real numbers, and for example, all set of real numbers form group under addition. By the way, if by chance anybody finds it as a new thing, then I would advise them to prove that all the four postulates are satisfied for these these examples. So, but when we go to multiplication, we have to exclude the zero, which is the identity under addition. So this we have to be a bit careful. I mean, similarly, complex number form group under under addition as well as under multiplication. Of course, this identity element has to be excluded. So once we there, then we see that vectors in a vector space also form group under simple simple addition. Here you have to be a bit careful, because like ordinary vector in a three-dimensional space, they form group under addition. It is very trivial to prove, but we can't show that we can't find that they form group under multiplication. Even the cross product and scalar product don't satisfy these things. So first time we are seeing something. I mean, what do I mean by that is, here I find a real number forming group under addition as well as multiplication. Same thing is true about complex number. Well, complex vectors form group under addition, but not under vector multiplication. So we have to be careful about that. In the same way, we find that M cross N matrices form group under matrix addition. All matrices which have same number of rows and same number of columns, that means all have same rows separately, all have same column separately, they form group under multiplication. However, when we are considering matrix multiplication, you can multiply different kind of matrices, but you want to satisfy the causal property unless both the number of rows and columns are same. So square matrices, where number of rows and columns are same, they form matrix. They form group under matrix multiplication. The only condition is they should be non-singular. That means their determinant should not be zero, because if determinant is zero, then you can't find the inverse. Everybody must have done this kind of exercise, and these n cross n matrix group is very essential for us, because when we go to quantum mechanics and actually discuss application of group theory and of course symmetries this way, we need such groups which are n cross n matrix group. So again, I repeat that there is no condition. Simple condition is they should be non-singular. These matrices can be real. They can be even, I mean, complex. So that is not a problem. We can have a group of n cross n real matrices. We can also have group of n cross n complex matrices under matrix multiplication. No other condition. So those will give us technically called a general linear group in n dimension and real dimension, or n and and complex dimensions. After that, we may keep on adding more and more condition. For example, if it is a real matrix, I can ask its inverse to be given by the transpose. That is what I will show you in the next slide. If it is a complex matrix, you may put unitarity condition, as I just shown you, that you find that is complex conjugate and transport done together, that behaves like the inverse of a matrix. And particularly, we will find that they are very useful tool to study rotations. So when we are looking at n cross n matrices, we have two ways of looking at their group. We can think of them just as a mathematical objects, matrices, nothing else, not much, not more, not less, not more. And they form a group. This is just a mathematical quantity. However, we can also use these matrices to perform rotations. I'm sure everybody must have learned this thing in classical mechanics by Goldstein or any good book on classical mechanics, that the rotations are given, described by matrices. However, when I say rotations form a group, I change the definition of multiplication. I say the rule of combination of rotation is we apply first rotation, then we apply the second rotation, and maybe the third, and so on and so forth. So this application of successive rotation is the language of composition. However, tools of matrices would be very much beneficial for this purpose. So let me go to the next slide where I give the illustration. In fact, this particular thing, if you see, you can find it in NCERT class 11 mathematics. In class 11 mathematics, what do? They use matrices to perform rotation of a two-dimensional vector. So suppose I have a two-dimensional vector in a real dimension with components x1 and x2, and I rotate this vector to another vector which is primed vector. Obviously, the prime vector in general would have different components, say x1 prime and x2 prime, and this rotation, because the length of the vector will not change, so it requires two things. One, that this rotation matrix Rij should satisfy the orthogonality condition. That means its transpose should, should be its inverse, and secondly, its determinant should be plus one. So that is all I mean when I say SO2. Two means two dimensional. I'm looking for a rotation in two dimensional space. So you don't have to be scared of SU2, SO2 words which will keep on actually repeating in these lectures. And O stand for orthogonal. It means this matrix which is performing the rotation, because everybody must be reminding that x1 prime was supposed to be x1 sine theta minus x2 sine theta, and similarly x2 is given by the combination of this, and it is a trivial exercise which I am leaving here for the students to show that the length of the vector does not change. And interestingly, this very matrix also shows that it is orthogonal because its transpose is going to be its inverse. So this also I am leaving as exercise. In fact, one can choose matrices of this kind and show that they satisfy all the four postulates. And this S word seems to be new, but this word means special. So it is these rotation or these matrices, they form, technically speaking, a SO2 group, that means special orthogonal group in two dimension. So special is nothing but a condition on the determinant of the matrix. It should be one, and you can trivially find it here that its determinant is cosine square theta plus sine square theta, which is equal to one. So this word S means its element is one, and O means this matrix R matrix satisfy the orthogonality property. That means the in transpose of this matrix is its inverse. This also can be shown. Obviously, you can also verify composition law and other laws. So once we see it, we can generalize it to three dimensional rotation. This is a very important topic which students might have studied in classical mechanics when they learn the Taylor angle, which describe three-dimensional rotation of a vector in terms of z-axis. First, they perform rotation about z-axis, then x-axis, then finally the new z-axis. But we don't have to stick to those kind of actually set of rotation. In general, you can describe a three-dimensional rotation in rotation of a vector in three dimensions with the help of three separate rotations. What we can do is we can perform a rotation about the z-axis with angle theta z and here. So this is nothing but enlargement of this 2 by 2 matrix by adding this third column and this third row. It is trivial to show that this particular matrix will mix a component, keep the z component unchanged. So if you understand this very well as a as an extension of this matrix, then we can write down a corresponding matrix for the rotation about the pi axis. So in this case, x and z component of new vector would be mixed again, and finally we now perform a rotation about the x. If you like, if you want to have a single matrix, no harm, you can multiply all these three matrices. That will give you one-time application on the three-dimensional real space vector, and will give you a new vector. So here, how many elements we have? Three. Whereas in two-dimensional space, only single element is there. this is an important place because how many parameters you need to perform a transformation also is decided by these actually conditions. These are called the rank of the groups. And here, this group will be known as SO3, special orthogonal group in three dimension. Because when you combine them together, we have a single matrix involving three angles: theta x, theta y, theta z, and three angles are required to, specify a general three-dimensional rotation. And because all of them are already satisfying the orthogonality condition, so their product will also satisfy the orthogonality condition. And because each of them has determinant one, it is obvious, and so the net determinant will also be one. So in this way, this extension of two-dimensional transformation to three-dimensional transformation of a vector, these rotations or transformation form a group with the help of the matrices. So that is why uh, what I mean is that we need to have a good understanding of matrices and their transformations law to go further. So I hope everybody is happy with this. By the way, just to complete the thing, sometimes SO3 group is written like R3 or R3 group R4 actually. These things rotation, that is all. So let me just help my younger friend to show that all the four group properties are actually satisfied, say by two-dimensional rotation. I can leave this as exercise for them for the case of three-dimensional rotations. So say in two-dimensional case, we have a matrix that is rotation given by angle theta 1. Same kind of a matrix where theta 1 is changed to theta 2. If I multiply them together, we have this. So only the value of the argument angle is changed. Otherwise, form of the matrix remains same. So if you choose this kind of a matrix, we find that the product is also of the same kind. Same thing can be done for the associativity. It is trivial to think here because first you multiply these two things will give you theta 1 plus theta 2. When you multiply with this, will have a matrix where angle will be replaced by theta 1 plus theta 2 plus theta 3. And same thing will also happen when you multiply second with third and then multiply with actually 1. Of course, these are matrices. We have to be bit careful about the order. Incidentally, SO2 group is technically saying it is abelian, and SO3 group is going to be non-abelian. This is abelian word is chosen to honor the great mathematician Abel. This basically means commutative, because such 2 cross 2 matrices also obey the commutative condition, but this is not an essential actually condition, because when we go to three-dimensional rotation, then matrices which are not satisfy commutation, so we have to be careful about the order. An identity element in this case correspond to when actually theta is 0. So this is a 2 cross 2 identity matrix, and it is trivial to show if you multiply it by any matrix, that matrix will not change. Now, if you replace theta by minus theta, that will give you the inverse. But accordingly, what you find is this is nothing but the transpose of this matrix. So if you multiply the two, you do get identity. So all the four properties of group are not satisfied. But what more I am expecting from this. Now it is going to be a little technical because I am going to apply it on quantum state. Though of course still we have many routes possible. One is we can use the language of, we can keep on using the language of matrices and treat the technically called a generator of the transformation in the form of matrices. Nothing wrong with that. In fact, we already see in angular momentum case, we can have a wave mechanical or differential representation of generators. We can also have the matrix representation of the generators. In fact, matrix operators gives us more more information, and I will talk about that also. But let me come back to the point. So suppose I restrict to the rotation about the z-axis. So the original vector x1, x2, x3 components is transformed to have new components x1 prime, x2 prime, x3 prime. This is an ordered space, so you don't have to worry. So suppose I get this new components. Obviously, x prime 3 will not change because it is a rotation about z-axis, but xy component will change. And so suppose I choose infinite similar rotation, that means I'm reducing them. Just let me check my battery if it is there. uh, yeah, it is 40 minutes, so I think I can continue. Oh, and by the way, we do not reduce generality. We do not lose actually generality by limiting to infinite rotation, because finite rotations can always be built up with a large number of infinite rotations. So it's okay. So when I do that, then you know that when phi is replaced by delta phi, sine phi becomes delta phi and cos phi becomes 1. So this is nothing but identity matrix plus another matrix, where only these two terms will be there. So either I move with that kind of a approach that will give us the matrix representation of the rotation, and finally their generators. And just as a quick reminder, if you have studied Goldstein, I I remember they talk about the generator of of rotation even for classical rotation. So you can refer back to that, and they are using the same kind of a language, and they also have corresponding Lee algebra, that is nothing but commutation relation between uh, the angular momentum generators. One way we can follow that. The another way is, suppose I want to study the effect of this rotation on the position vector r, on which the wave function depends. So suppose I choose a wave function of a quantum system, and I change its position vector r to r prime. I want to know what it does to the overall actually wave function. And what you need to do is nothing but Taylor series expansion. You have to be a little bit careful. I'm sure many of you, probably all, must have done similar thing for space translation as well as for time translation. Simply expand the things as the Taylor series and show that position change in space can be understood with the help of, I mean, space translation can be generated by the linear momentum operator, and similarly time translations are actually generated by energy operator. Using the same kind of mathematics, one can show that under rotation of this kind, the action of such operator upon the wave function would be to give you 1 plus a delta phi multiply with this. That is x1 into derivative with respect to x2 minus x2, and derivative of, with respect to x1. So if you apply this to psi, we have a new wave function with different position vector r prime. R prime, again I remind you, are actually connected to R with the help of these, or maybe these uh, I mean transformation. So this everybody can recognize here is the same to be nothing but third component of the orbital angular momentum. You know, L, the orbital angular momentum is given by R cross P. So if you choose its a third component, you have this. Of course, H you have to properly take care. So this part I am leaving as an exercise for students to uh, I mean, prove. So once you see it for three-dimensional case, it is a trivial job to go for arbitrary rotation, because in the last to last sheet I have shown you that a general rotation of vector can be described by a product of three effectively two-dimensional but along different axes, actually three rotations. So that is all you have to do. So this can be then generalized. This form can be generalized to this form. So what is the change? Here you have only this L3, that is the third component of the orbital angular momentum. So if you perform rotation about y-axis, similarly we will have a term where delta phi may be different, and we will have L2 component, and for rotation about x-axis we will have another angle, third angle, and the angular momentum operator along the x direction. So if you add all the three terms together, we will have identity plus this iota is ordinary iota minus 1 under the root, so do not confuse it with other thing. Delta phi k dot lk, here you are actually multiplying them. So if you use the vector language, then it is delta phi vector dot L vector, or in a component form I have explicitly mentioned here, and sum over k is given here. So this is going to be the rotation operator giving you wave function psi prime, psi r prime. This is how actually connected to old psi r. So the angular momentum operator act as the generator of rotation in three dimension. By the way, some of you might be still worrying. I am showing it only for the case of infinitesimal rotation. Why not for the finite? This also I can leave as an exercise, because what you do is you add more terms. If you have infinitely many terms where you have delta phi square, and delta phi cube, and all the higher order term, that Taylor series term can be replaced with exponential with this value of the exponent. So you will have a transformation which is given by exponential with exponent iota delta phi dot L vector over the H vector. So that will give you the finite transformation, because you have kept all the terms. Obviously, that infinite series is basically reduced to only two terms when we have very small value for the rotation. So these are small things, and this is part of the book. By the way, I again remind you that this actually surprises me that we find here connection between rotation and the angular momentum operator. When we discuss angular momentum algebra in quantum physics, rarely I find people actually talking about group. So I often tell my student that if you have done orbital angular momentum algebra thoroughly well, and then of course one can use it the same operators for spin also, you will never have any problem with the group theory or its application. So again, I will finally clump the whole thing together. But let me remind you what we have done about orbital angular momentum algebra, which we first time come across when we study hydrogen atom. You don't have to stick to hydrogen atom. In fact, any problem where potential is spherically symmetric, center potential, we obviously will have these kind of things appearing. We may have three-dimensional harmonic oscillator, we may have hydrogen atom. Even you can solve a free particle Schrödinger equation using the spherical coordinates. So when we go to spherical coordinates, we have to do little more things. But before that, let me remind you what are the angular momentum operators. This is just the same thing. We know that linear momentum components px, py, pz are given by these operators, and it is a simple exercise to show that angular momentum operators which are nothing but components of R cross P, cross product of R and P, they operators satisfy this kind of a commutation relation, where Lx Ly commutator gives you IH Lz. In fact, don't ignore this commutation relation, because for every group, these commutation relations are going to form the backbone of everything. So it is nothing but commutator of operators which act as the generator of transformation. So we have a transformation group which is generated by a certain number of operators. We have to carefully tackle those operators. So first of all, what we do is we find out their commutation relation. This I'm sure everybody must be remembering. It is Lx Ly minus Ly Lx, which is nothing but linear combination of the operators themselves. Incidentally, here only one component appear. So there are many ways of writing this. One is Lx Ly giving you IH cross Lz, and it's a cyclic term. Or sometimes formally people write here Li Lj equal to I epsilon Ijk Lk, and some other k is there, and those epsilon Ijk are Levi-Civita symbol. I have avoided that just to show, just to keep the things simple. But what more you can do? What you do is you realize that out of these three, because they don't commute totally, so only one of them can be diagonalized. Only one of them can act as the there is a slip. This has actually shifted. So what I am doing here, I am actually looking for Hermitian operators which can act as the eigen operator. So only one of these three can be chosen to be the eigen. I could have chosen Lx Ly also, but it is a convention to choose Lz to be the eigen operator, and that will its quantum number or its eigenvalues will be used to designate the states. But besides the Lz, it is interesting thing to note that if I construct a operator using the squares, or in higher groups, even cubes and higher powers, but here it is only the squares, and add them, that is like total angular momentum uh, length square, Lx square plus Ly square plus Lz square. This operator is unique in the sense it commutes with all the three Lx, Ly, Lz operators. So the advantage of that is, along with Lz, I can also diagonalize L square. It means L square as well as Lz both together are they are forming the set of eigen operator whose eigenvalues will be used to designate the states. Basically, a reminder of this algebra, which I'm sure every student must have done, particularly when studying at MSc level. But part of these things are certainly done in quantum mechanics, BSc, maybe part 2 or 3. So we have, again, okay, let me quickly remind, out of the three operators, one Lz, say, and some of their squares. Technically, we will call them Casimir operators. L square is an example of Casimir operator in the name of the person who worked. So where are the other two operators gone? So L square and Lz are acting as eigenoperators because they are Hermitian. But where have gone Lx, Ly? What we do, we construct a linear combination of Lx and Ly like this. So suppose I have Lx and Ly, I add them like this: Lx plus ida Ly, that I call L plus. Similarly, L minus is Lx minus ida Ly. They will be used as the shift operators. So whatever I'm doing here is applicable almost all geometry groups which we need in the application to particle physics. So we have this set of operators. But suppose I change the coordinate system. I go from Cartesian to spherical coordinate system, which is in a way compulsory for us to go, because any system, any quantum system where potential is spherically symmetric, it is always advantageous to go to spherical coordinates. In that case, what I find that Lz becomes nothing but minus IH derivative with respect to phi, and L square becomes this combination. See, nowhere R and R actually appear here, or derivative with respect to R appear here. All are involving derivative with respect to theta and phi. So this ensure, what it actually ensure, the Hamiltonian of the system, say the hydrogen atom, where we have kinetic energy term b square by 2m minus e square by r, which is spherically symmetric, that is central potential. So any quantum system described by um, a spherically symmetric potential, in that case, Hamiltonian will obviously commute with Lz as well as with L plus minus, because L plus minus also involve derivative with respect to theta and phi. It is a small exercise which I can leave to the students to show that angular momentum operator looks like these in the case of spherical coordinates. And I'm sure if they have solved hydrogen atom at BSc level, they must have done this kind of exercise. So that is the beauty, that you immediately see a potential does not involve theta and phi. The Hamiltonian of the system must it does commute with all the angular momentum operator as well as its L square. And in such a situation, we find the spherical harmonics naturally are the eigenstates of these operators. YLM theta, there are two ways. Either you start with YLM theta and apply the operator and convince, or the ab initio method is you write down the Hamiltonian of hydrogen atom in terms of del square and r theta phi coordinates and perform the separation of variable technique, handle the phi part and theta part. Phi part will simply give you exponential I phi term, and the the other part will come as a uh, legendary, I mean, polynomial, associated legendary polynomial. And if you combine the two and put the normalization factor, that is nothing but spherical harmonics. So these spherical harmonics are natural eigenstates for Lz with 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 eigenvalue mh, and for L square we have the eigenvalue L into L plus 1. In fact, it is a very useful and interesting to note. You don't have to restrict the such states for the item, for the hydrogen atom. And as I have been repeating, as long as potential is spherically symmetric, it may have any algebraic form, but it does not involve theta and phi. In that case, the angular part is always given by spherical harmonics, whether it is a free particle Schrodinger case, or it is a harmonic oscillator, or it is a Coulomb potential term, or even a combination of them. In fact, as long as potential does not involve theta and phi, this phenomena will occur. So the angular part is immediately given by LM theta. But we have to also realize the application of shift operator, because the, these two eigenvalues L and M, they uh, they are used to designate the eigenstates. So these multiplets which are formed by these uh, these 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 multiplets are formed by uh, these two quantum numbers. This very concept is very important, because when we go to I mean particle physics or regular physics also, we find isosphene multiplets, SU3 multiplets. So this understanding of multiplex must be made clear at this point, that eigenvalues of eigen operators, Hermitian operators, which are the member of the angular momentum operator, and Casimir-like operators, that is L square, constituted from them, their eigenvalues are used to designate the multiplets. So what are the restriction upon L? Only 1, 0, 1, 2. This is what we do when we solve the Legendre differential equation. Associated Legendre differential equation also asks us to demand M to go from minus L to L. Of course, they obey the quantization principle. So we have all values starting from minus L to L. Obviously, the multiplicity of the set is 2L plus 1. Those are the number of states. And if you remember the connection between symmetry and degeneracy, we can immediately reach at a conclusion that all the states of hydrogen atom for fixed L varying M minus L to L will be degenerate. Why? Because these states are mutually connected with the help of the shift operators, and shift operators also commute with the Hamiltonian. And remember that these three components of angular momentum operator acting as the generator of three-dimensional rotation. So if space is isotropic, when we go to wave function, we find that these LZ are used to perform rotation upon the wave functions, and they
Sir, hello?
yes,
Hello?
please. Yeah.
Yeah, we are not able to get your signal, sir.
What is happening? Can you help me in this? Because to me things looks all right.
Okay.
Maybe
Is everybody able to hear, sir? Uh, just 1 second, sir.
Yes, sir. Yes, sir.
All of you are able to hear, sir?
You are
The
now unmuted.
sir's video get paused, sir.
Yeah, that's what sir's video got paused, right? Yeah.
Because this seems to be sharing my video. Okay, no, that's not a problem. Capcom is, I mean,
Yeah, sir, maybe you can just cut off the video and restart it.
where?
You
Which,
can,
like,
sir, you can just that video you switch off, sir, once and then restart it.
oh, how to
Lalit,
do it? I mean,
actually,
I have to stop sharing. I have to stop sharing
webcam.
webcam. Okay.
Yes, sir. And then restart it, sir.
It is not responding.
Okay, sir. So either way, I think it's a good place to stop. It's already 1 hour.
Fine, yeah. So then I will continue with this orbital angular momentum algebra.
Tomorrow, sir. Yes, sir. Yes, sir.
Yeah, tomorrow or maybe next Monday, as you say.
Yeah, whatever you feel, sir. Are you ready for tomorrow? Then we can have a lecture tomorrow also. I think.
I can, but the only thing I worry is next Sunday probably we have a Dashara, so might be some students.
All are at home only, sir. All the students are at home.
Fine, there is no problem.
Yeah. Is it all okay for all of you to have a lecture tomorrow? Let's take a poll, sir.
Yes, sir. Sure, sir.
Should we have an? All of you just say yes or no. Don't